Each day you wake up and do your daily routine and move on with life. But have you ever stopped to think about what is happening in your brain while you do the things you consider normal? If we are going to learn about the processes that occur in the brain throughout the day, then we need to first learn about the basics of the brain. The brain is the most complex part of the human body. This 3-pound organ is a seat of intelligence, interpreter of the senses, initiator of body movement, and controller of behavior. Lying in its bony shell and washed by its protective fluid, the brain is the source of all qualities that define our humanity. The brain is the crown jewel of the human body. For centuries, scientists and philosophers have been fascinated by the brain, but until recently, they viewed the brain as nearly incomprehensible. Now, however, the brain is beginning to relinquish its secrets. Scientists have learned more about the brain in the last 10 years than in all previous centuries because of the accelerating pace of research in neurological and behavioral science and the development of new technologies. As a result, Congress named the 1990s the decade of the brain. At the forefront of the research on the brain and other elements of the nervous system is the National Institute of Neurological Disorders and Strokes (NINDS), which conducts and supports scientific studies in the United States and around the world. The brain is like a committee of experts. All the parts of the brain work together, but each part has its own special properties. The brain can be divided into three basic units: the forebrain, the midbrain, and the hindbrain. The hindbrain includes the upper part of the spinal cord, the brainstem, and a wrinkled ball of tissue called the cerebellum. The hindbrain controls the body's vital functions such as respiration and heart rate. The cerebellum coordinates movement and is involved in learned rote movements. When you play the piano or hit a tennis ball, you are activating the cerebellum. The uppermost part of the brainstem is the midbrain, which controls some reflex actions and is part of the circuit involved in the control of eye movements and other voluntary movements. The forebrain is the largest and most highly developed part of the human brain. It consists primarily of the cerebrum and the structures hidden beneath it. When people see pictures of the brain, it is usually the cerebrum that they notice. The cerebrum sits at the topmost part of the brain and is the source of intellectual activities. It holds your memories, allows you to plan, enables you to imagine and think. It allows you to recognize friends, read books, and play games. The cerebrum is split into two halves or hemispheres by a deep fissure. Despite the split, the two cerebral hemispheres communicate with each other through a thick tract of nerve fibers that lies at the base of this fissure. Although the two hemispheres seem to be mirror images of each other, they are different. For instance, the ability to form words seems to lie primarily in the left hemisphere, while the right hemisphere seems to control many abstract reasoning skills. Each cerebral hemisphere can be divided into sections or lobes, each of which specializes in different functions. To understand each lobe and its specialty, we will take a tour of the cerebral hemisphere, starting with the two frontal lobes, which lie directly behind the forehead. When you plan a schedule, imagine the future, or use reasoned arguments, these two lobes do much of the work. One of the ways the frontal lobe seems to do these things is by acting as short-term storage sites, allowing one idea to be kept in the mind while other ideas are considered. In the rearmost portion of the frontal lobe is a motor area, which helps control voluntary movement. A nearby place on the left frontal lobe, called Broca's area, allows for thoughts to be transformed into words. When you enjoy a good meal, the taste, aroma, and the texture of the food, two sections behind the frontal lobe called the parietal lobes are at work. The forward parts of these lobes, just behind the motor areas, are the primary sensory areas. These parts receive information about temperature, taste, touch, and movement from the rest of the body. Reading and arithmetic also functions in the repertoire of each parietal lobe. As you look at the world around you, two areas in the back of the brain are at work. These lobes are called the occipital lobes. Process images from the eyes and link that information with images stored in the memory. Damage to these occipital lobes can cause blindness. The last lobes on our tour of the cerebral hemispheres are the temporal lobes, which lie in the front of the visual areas and nest under the parietal and frontal lobes. When you appreciate symphonies or rock bands, your brain responds through the activity of these lobes. At the top of each temporal lobe is an area responsible for receiving information from the ears. The underside of each temporal lobe plays a crucial role in forming and retrieving memories, including those associated with music. Other parts of this lobe seem to integrate memories and sensations of touch, sound, sight, and taste. Coating the surface of the cerebrum and the cerebellum is a vital layer of tissue. The thickness of a stack of 2 or 3 dimes is called the cortex, from the Latin word for bark. Most of the actual information processing in the brain takes place in the cerebral cortex. Where people talk about gray matter in the brain, they're talking about this thin rind. The cortex is gray because nerves in this area lack the insulation that makes most of the other parts appear to be white. The folds in the brain add to its surface area and therefore increase the amount of gray matter and the quantity of information that can be processed. Deep within the brain, hidden from you, lie structures that are the gatekeepers between the spinal cord and the cerebral hemispheres. These structures not only determine our emotional state, they also modify our perceptions and responses depending on that state, and allow us to initiate movements that you make without thinking about them. Like the lobes in the cerebral hemispheres, the structures described below come in pairs. Each is duplicated in opposite halves of the brain. The hypothalamus, about the size of a pearl, directs a multitude of important functions. It wakes you up in the morning, gets your adrenaline flowing during a test or a job interview. The hypothalamus is also an important emotional center, controlling the molecules that make you feel exhilarated, angry, or unhappy. Near the hypothalamus lies the thalamus, a major clearinghouse for the information going to and from the spinal cord and the cerebrum. Waking up in the morning. The hypothalamus isn't the only thing that helps us wake up in the morning. There are at least 9, although definitely more, neurotransmitters and hormones that play key roles in the sleep and wake cycle. The first neurotransmitter is GABA. GABA is one of the most prevalent neurotransmitters in the brain and is usually responsible for inhibition. GABA releases is often seen as a way to shut down or regulate neurons. One of the main areas GABA is involved in for sleep-wake cycle is the posterior hypothalamus. The stimulation of the neurons in the PH are known to contribute to wakefulness. It has been seen that increased levels of GABA in this area contribute to inducing sleep. The second neurotransmitter is orexin. It is thought that orexin is responsible for regulating many different systems involved with sleep and stabilizing both awake and sleep states. Some of the systems orexin regulates are dopamine, norepinephrine, histamine, and acetylcholine systems. It is also thought that the orexin system is responsible for integrating different influences such as metabolic, circadian, and sleep depth to decide what state the body should be in, asleep or awake. The third neurotransmitter is glutarate. Glutarate is involved in a variety of areas of the sleep and wake cycle. Glutamatergic input to the oral part of the pontine reticular formation (PNO) is thought to regulate sleep duration. It has also been seen that glutamatergic inputs in the posterior hypothalamus region help regulate both REM sleep and wakefulness. The fourth neurotransmitter is acetylcholine. The most important ACH neurons that are involved in the sleep-wake cycle are located in the pons and basal forebrain. It has been seen that the ACH neurons in these areas are very important for the initiation of REM sleep. It has also been observed that ACH levels are at their highest during REM sleep and waking states. The fifth neurotransmitter is norepinephrine. Norepinephrine's activity in the locus coeruleus is the most important with regards to the sleep-wake cycle. This is one of the main areas involved in arousal from sleep. Increased norepinephrine also decreases REM sleep. The sixth neurotransmitter is dopamine. Dopamine seems to regulate sleep-wake states and control when we enter each. Dopamine can also regulate melatonin, which is partly responsible for causing sleepiness, which can greatly contribute towards waking up from sleep. The seventh neurotransmitter is melatonin. Melatonin levels are high at night, during sleep, and low during the day. The levels of melatonin are regulated by suprachiasmatic nucleus of the hypothalamus, which reacts to the amount of light in the environment. So the darker it is outside, the more melatonin there is. The eighth neurotransmitter is serotonin. Serotonin has similar effects on the sleep-wake cycle to those of the norepinephrine. Serotonin helps to maintain arousal and cortical responsiveness, as well as inhibiting REM sleep. The ninth neurotransmitter is adenosine. Adenosine is an inhibitory neurotransmitter that is involved in promoting sleep. After you wake up, adenosine levels begin to build up in your brain throughout the day, causing you to become more and more sleepy. People throughout history have tried to fight this by taking adenosine antagonists, which block the sites where adenosine normally binds to the brain. The most common of the adenosine antagonists is caffeine. Although there are many more neurotransmitters and hormones involved in the sleep-wake process, these are the most important ones involved. The afternoon slump. It's 3 p.m. and you find yourself struggling to focus on work. You can't seem to stop checking Facebook. Instead of being productive, you welcome distractions like text messages and coworkers coming by to chat. Welcome to the afternoon slump, the time in your workday when your brain refuses to cooperate with you and can't stop procrastinating. Why can't you focus in the afternoon? There are many important reasons for feeling the mid-afternoon slump. According to a study by Gallup, 40% of Americans don't get enough sleep. Getting enough sleep is a cornerstone habit that has many positive effects. Mental and physical performance improvements among them. If you're not getting enough sleep, your brain is not functioning optimally. Research also points to our circadian systems as a cause of mid-afternoon slump. Our mental performance ebbs and flows throughout the day. Whatever the reason of your lack of afternoon focus, eat something, but make sure it has one thing, glucose, to help you break out of your daily slump and finish your day strong. Circadian rhythms are regular changes in mental and physical characteristics that occur in the course of a day. Circadian is Latin for around a day. Most circadian rhythms are controlled by the body's biological clock. This clock, called the suprachiasmatic nucleus, or SCN, is actually a pair of pinhead-sized brain structures that together contain about 20,000 neurons. The SCN rests in the hypothalamus. Signals from the SCN travel to several brain regions, including the pineal gland, which responds to light-induced signals by switching off production of the hormone melatonin. The body's level of melatonin normally increases after darkness, making people feel drowsy. The SCN also governs functions that are synchronized with the sleep-wake cycle, including body temperature, hormone secretion, urine production, and changes in blood pressure. By depriving people of light and other external time cues, scientists have learned that most people's biological clocks work on a 25-hour cycle rather than a 24-hour one. But because sunlight or other bright lights can reset the SCN, our biological cycles normally follow the 24-hour cycle of the sun, rather than our innate cycle. Circadian rhythms can be affected to some degree by almost any kind of external time cue, such as the beeping of your alarm clock, the clatter of a garbage can, or the timing of your meals. Scientists call external time cues Zeitgeisters, German for time givers. Have you ever crossed time zones? If you have, you probably have suffered from jet lag. You will feel tired when the alarm rings at 8 a.m. the next morning because according to your body's clock, it is still 5 a.m. It usually takes several days for your body's cycles to adjust to the new time. Symptoms much like jet lag are common in people who work nights or perform shift work because these people's work schedules are at odds with powerful sleep-regulating cues like sunlight. They often become uncontrollably drowsy during work, and they may suffer insomnia, or other problems when they try to sleep. Shift workers have an increased risk of heart problems, digestive disturbances, and other emotional and mental problems, all of which may be related to their sleeping problems. The number and severity of workplace accidents also tend to increase during the night shift. Major industrial accidents attributed partly to the errors made by fatigued night shift workers include the Exxon Valdez oil spill and the Three Mile Island and the Chernobyl nuclear power plant accidents. REM sleep. We've all heard of REM, rapid eye movement, discovered by the late physiologists Eugene Asursinski and Nathaniel Kleitman at the University of Chicago in 1953. During REM sleep, our brain waves, the oscillating electromagnetic signals that come from the large brain activity, look similar to those produced while we are awake. So it became clear that the sleeping brain was not merely resting, either in REM sleep or in slow wave sleep. Sleep was doing something different. Sleep was doing something active. Discovering REM sleep was the first clue that sleep didn't just help our bodies keep our bodies healthy, but also our minds. But wait, sleep does even more than keep our bodies and minds healthy. Even more recent research suggests that our sleep helps our brain to process the information of the day and solve problems. The upshot is that sleep is far, far more important than most of us realize and few of us appreciate. We miss it, thinking nothing of chopping off a few hours here and there, but the emerging research suggests that when we cut out sleep, we may be actually harming our formation of new memories from the recent past and our ability to perform up to our usual standards. The researchers sum it up best. As exciting findings such as these come in more and more rapidly, we're becoming sure of one thing. While we sleep, our brain is anything but inactive. It is now clear that sleep can consolidate memories by enhancing and stabilizing them, and by finding patterns within studied material, even when we do not know that patterns might be there. It is also obvious that skimping on sleep stymies these crucial cognitive processes. Some aspects of memory consolidation only happen with more than 6 hours of sleep. Miss a night, and the day's memories might be compromised. An unsettling thought in our fast-paced, sleep-deprived society. Thank you so much for listening to this podcast about the brain throughout the day by Ashish Bomasani.